You got how to do, right? Hmm? You got how to do. Nothing here.
So I hope my screen visual to all of you. Yes, sir. Can you hear me?
Yes, sir. Yes, sir.
Okay.
Are you getting my voice, sir?
Yes, yes.
Yeah, yeah. Now it's good. Your PPT is also visible.
Okay, sir.
Sir, we'll start just by 5 to 8 minutes.
Okay, sir.
Yes, sir. Just be here to when session starts. No, till understand my feeling for this. No, 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 don't escape. Just unmute.
Yeah, hello. Sir, can we start the session?
Hello.
Yeah, hello. Yeah, hello.
Hello, sir.
Yes, ma'am.
Am I audible to you?
Yes, ma'am. Yes, ma'am. You're audible.
Yes, sir. Before starting the session, I would like to give a brief introduction of yourself.
Okay, ma'am.
Good afternoon, everyone. So, for today's session, webinar on atomic scale modeling using synopsis, our speaker, Engineer Deepak Upadhyay is there. Let me give a brief about him. He has completed his BTech from Electronics and Communication Engineering from Dr. APJ Abdul Kalam Technical University, Lucknow, Uttar Pradesh. He has worked at Levy Design at Consultant India Private Limited, Gurgaon, as a junior design engineer. He has also worked at Impulse Technology, Gurgaon, as application engineer. Now he's working in Integrated Microsystem as application engineer, currently working on EDA tool called as Synopsys Quantum ATK. Today he will show the presentation and demonstration on nanoscale material and device simulation by DFT and DFT plus NEGF quantum transport support method using quantum ATK software and its application in current and future technology. Sir, may I now invite you for your talk?
Yeah, thank you for this brief introduction. So I would like to thanks to organizing committee who organized this beautiful session, and also I would like to thanks. Yeah, hello. Can you hear me?
Hello. Yeah, sir. Start.
Hello. Yes, sir. Okay,
Yeah,
sir.
yeah. Start, sir. Yeah.
So I would like to thanks all the organizing committee who organized this beautiful session, and also a special thank to Kamal Solanki for inviting me to the Atal Faculty Development Program for the next generation VLSI design integrating novel memory element and the nanomaterials for the advanced application. So I am honored to have the opportunity to showcase this synopsis quantum ATK for the atomic scale simulation. So we will proceed with the presentation where I will show you some brief features and the capability of this software, and we will then proceed with the live demonstration on this tool, and then we will end the session with the question and answer. So let's get start this session. So if we talk about this quantum ATK, so this quantum ATK is an integrated platform of the electronics and atomic scale modeling tools, and this quantum ATK is written in Python and C++. So this quantum ATK is developed by the expert software engineers and scientists to meet the highest requirement of usability and efficiency. So this quantum ATK gives you to access a powerful set of simulation engine for the research and development at the atomic scale. So it comes with the four simulation engine. So we have the density function theory. We also have the semi-empirical tight bonding model. And for the large scale simulation, we have the classical and the machine learned force field simulation. And for the devices simulation, we have the non-equivalent green function method that will combine with the density function theory, and also you can combine it with the semi-empirical tight bonding model. So this quantum HK gives you to complete solution for the material as well as device modelings with the multiple atomistic method implemented in a single platform. So this quantum ATK is a comprehensive platform for the atomic scale material and device modeling tools. We also offer effective tools for achieving realistic outcomes, and we also offer a synergistic solution to solve the complex problems. Now, if we talk about the bigger application of this tool, so the bigger application of this tool for the molecular structure simulation, surface simulation, interface between different geometry and different symmetry, devices simulation, complex material like hexagonal, tetragonal, triplex, phosphorus materials, polymers and composite materials, even nanostructure like the nanotube, nanoribbon, nanowires that you can easily simulate by using this quantum ATK. So this quantum ATK comes with the sophisticated graphical user interface where we have the molecule builder. So any kind of molecule you can design, either it could be an inorganic molecule, either it could be organic molecules. And we also have the surface builder. So for creating any kind of surface structure, basically we need to define the Miller indices. So their scale value we need to define either 100, 101, 111. So whatever the combination you want to create the surface, just define the Miller indices, and then the software will automatically create the surface structure. And even the interface between two material and more than two material, that is also possible. And if we talk about the device application, so in this quantum ATK we support the 1-flow device structure, 2-flow device structure, even 3-flow device structure you can easily simulate, like the MOSFET and transistors. So these are the bigger applications where you can utilize this quantum ATK. So with this quantum ATK, one can model a wide range of atomic physical system, including molecules, polymers, 1D and 2D materials, any kind of crystal structure, amorphous materials, interface and multiple layer structures, and even devices simulation that you can easily create. And it also comes, we also offer a tailored GUI tools to build and visualize such models, set up the script, manage the local and remote machine, and also the analysis of the result. That all comes in a single GUI that is called Virtual NanoLabs. So here you can see we have the building tools that will basically help you to create any kind of structure. Either you can create the molecules, crystal, devices, and we also have the database of the material. So in this quantum ATK software, we have two options to import the material. Either you can import the material from the local database that exists inside the software, and we also have the online database. So where we support the crystallography open source database, and we also support the material project. And once you create your structure, you can go to the calculation setup that will be possible from the workflow builder, where you need to set up the calculation engine like the DFT-LCO, DFT plane wave, semi-empirical tight bonding models, and the classical force field and the machine learned force field simulation. In the meantime, you can also select your analysis part like their electrical properties, electronics properties, optical properties, thermal properties. So whatever the property you want to simulate, you need to add in the workflow, and then you can go to the job submission settings. So in the job submission setting, basically we need to fire the job from the GUI to the local machine. You can also fire the job from GUI to the remote machine. And then you can do the various insightful analysis like their band structure, density of state, phonon band structure, electron density, and also it comes with the visualization tools. So once you've done the simulation, you will get the output that you can visualize from our visualizer, either in 1D view, 2D view, and 3D view. And it also comes with the Python scripting. So if you are exporting writing the Python script, then you can write your own script in the editors. And if you are not aware of the Python scripting, then you can easily create the structure in the builder. Then you can go to the workflow setups where you need to add the calculator analysis part, and then you can do the simulation. Here you can see this is a brief description about the simulation engine. So it comes with the DFT plane wave method, DFT linear combination of atomic orbital, semi-empirical tight bonding models. And for the large scale simulation, we have the classical force field and the machine learned force field simulation. So if we talk about this DFT plane wave method, so by using this DFT plane wave method, you can study the electronics property of the periodic quantum system within the framework of DFT by using the plane wave basis set. If we talk about the DFT-LCO method, so you can study the electronics property of the closed and open quantum system within the framework of density function theory by using the numerical ALCO basis set. And if we talk about the semi-empirical tight bonding model, so you can study the electronics property of the molecules, crystal, and devices by using the self-consistent and non-self-consistent tight bonding models. And even the integration of this Synopsys CentOS ticket with the Synopsys Quantum ATK, you can easily integrate. So in this slide, you can see we have compared both the basis set. So we have the plane wave basis set and we have the linear combination of atomic orbital basis set. So if we talk about the plane wave basis set, so basically it is designed for the periodic world system and it is conceptually simple and it allows systematic convergence. Basically, it will require many functions per atom to achieve a good accuracy. In case of a LCO basis set, it is allowed for the non-periodic boundary condition and it is very efficient. In the LCO basis set, there is a large reduction of CPU times and memory as compared to the plane wave basis set. So this is the graph over the simulation time with respect to system size. So we have compared the hybrid function DFT LCO for the large scale system. So you can see we have the DFT plane wave with the hybrid function method, and we also have the DFT LCO with the hybrid function method. So in case of DFT plane wave with the hybrid function method, you can see the graph will exponentially increase. So at a fixed system size, it will require many times to achieve a good accuracy. But in case of DFT LCO with the hybrid function, we can achieve a linear scaling for this hybrid LCO method with respect to system size. So here you can see this is the pictorial representation of both the basis set. So in case of hybrid function with the LCO method, we can calculate our structure within an hour or minute something. And if we talk about the hybrid function with the plane wave method, so basically it will require a day or 2 days to get the simulation result. So the conclusion is that the hybrid function DFT LCO is up to 10x to 100x faster than the DFT plane wave method. Now it also comes with the DFT plus non-equilibrium green function method for simulating the realistic interfaces and surface structure. So this DFT plus NAGF method is an accurate tool to study the interface and the electronic devices. So here you can see we have the two probe device structure where we have the left electrode, right electrode, and we also have the center region. So not only the two probe device structure, even three probe device structure you can easily simulate, and then you can define their biasing voltage, gate voltage, so that you can simulate their resistance, capacitance, and their IV characteristics. And this NEGF method you can combine with the linear combination of atomic orbital, LCO basis set, and you can also combine with the plane wave basis set, and even you can also combine with the semi-empirical tight bonding models. Now this quantum HK also comes with the battery modules. So even you can also design the battery like the sodium ion, lithium air battery, and then you can study their cathode materials by using the multi-model computational approach like the DFT, semi-empirical, classical force field, and the Meissner force field simulation. And you can also obtain the lithium ion diffusion path and rate by using the combination of techniques like the energy elastic band, and also the harmonic transition state theory, and also the adaptive Monte Carlo simulation. Now, if we talk about the bigger application of this quantum HK software, so it covers a wide range of applications starting from the material to devices. So if you talk about the semiconductor application, so user can study the property of new material, interface structure, contact and stacks, and their impact on the logic memory devices. And if you talk about the battery material, so user can design the novel battery material for the cathode and anode, liquid and solid electrolyte materials. And even you can also calculate the open circuit voltage. And if you talk about the solar cell simulation, so you can design the novel photovoltaic materials and even the devices with the improved photocurrent. So you can follow the standard solar cell spectrum in the center region, and then you can study the various electrical properties. And if we talk about the polymer simulation, so you can design the polymer with the improved thermomechanical, thermoconductivity, and the optical properties. And even the catalysis, metal, ceramic, and glasses, that is also possible. Now, if we talk about the simulation procedure in this quantum HK, so typically you need to create your structure in the builder. So any kind of structure you can create, and then you can go to the setup that will be possible from the workflow builder. So you need to set up your calculator. Like you can see, we have the DFT LCO, DFT plane wave, semi-empirical, and also the classical force field and the Meissner force field simulation. In the meantime, you can also select your analysis part, and then you can go to the run option. So that will be possible from the job submission settings, where you can fire the job from the GUI to the local machine, either remote machine. And once you've done the simulation, then you can visualize your structure by using the visualizer tool, either in 1D view, 2D view, and 3D view. So it also comes with the machine learned force field simulation. So the question arises, why do we need this machine learned force field simulation? So the machine learned force field simulation is an accurate dynamical modeling tools for the complex structure generation, mechanical properties, thermal properties, electron phonon scattering, diffusions, and also the process simulation by the atomic layer deposition and the etching layer deposition. And other dynamical tools that is typically limited to 100 atoms due to the turnaround limitation times. But most of the industry requires 10,000 plus atoms to be simulated at a single time, and that is not practical with the quantum-based method because of their quality of resources and also the turnaround limitation times. So for the atomistic modeling, so we typically work within the three types of models that will provide the different level of accuracy at the different computational cost. So at the low level, you can see we have the traditional force field, which is very efficient but often lacking quality of resources. And in the middle, we have the semi-empirical models like the tight bonding energy. It can provide the higher accuracy at a higher computational cost. At the top, you can see we have the ab initio method like the density function theory, which can provide the higher accuracy, but at the increased turnaround limitation times. So here we have the machine learned force field simulation, which will allow you to train a potential to reproduce ab initio result at the low computational cost, similar to the traditional force field. So here you can see we have simulated a amorphous HF40 structure, and in this structure we have total 96 atoms. We have performed 50 molecular dynamic steps at 16 core. So in case of DFT with the molecular dynamic simulation, you can see it has taken 3 hours, 21 minutes and 27 seconds. And by using this MTP, that is a moment tensor potential, it is a part of machine learning technique. It has taken 10 seconds, and by using the classical force field, it has taken 9 seconds. But we will get the maximum accuracy and with the low computational cost by using the machine learned force field technique. So these are the some machine learned force field application where you can use this MTP moment tensor potential for the structure of the complex crystal and the amorphous materials, structure of the multiple layer stack, formation of the defect cluster, interdiffusion, defect diffusion, thermal transport, crystallization, and also the amorphization. So this quantum ATK comes with the sophisticated graphical user interface that is called Virtual NanoLab. So this graphical user interface is very easy to use, and also it comes with the Python programming interface that will enable the experienced user to efficiently implement the complex workflow, and also you can perform the advanced data analysis. So here you can see this is a screenshot of this graphical user interface that we will cover in the live demonstration. Now you can see we have the data, we have the builder, we have the workflow builder, we have the job submission settings, we have the editors, we have the viewer, and also we have the custom script, and we have the database of the material. Now, if we talk about some advanced analysis so that a user can study in this quantum ATK, so we also support the molecular dynamic simulation. So we have both, like we have the classical molecular dynamic simulation, and we also have the ab initio molecular dynamic simulation by using the different techniques like the NVT, NPT, stress strain, Langevin, and also you can optimize your geometry and also the optimization for the devices that is also possible. You can also do the dynamical matrix, Hamiltonian derivative, charge point defect, even the polymer simulation that is also possible. Now these are the some listed computable characteristics for the material and devices that user can study in this quantum ATK, like the band structure, Bloch state, boron effective charge, chemical potential, complex band structure, density of state, phonon band structure, optical spectrum, and also the projected density of state, Raman spectrum, photocurrent. So these are the list of computable characteristics. So if we talk about the job manager, so job manager is basically responsible to run the job from GUI to the local machine at the remote machine. So in the local machine, we support the serial, threaded, and the parallel for the faster simulation. We also support the remote submission mode like the TOR, PBS, Ancelerum, SG, LSF, and also the direct execution. So if we talk about the system requirement, so for using this Synopsys Quantum ATK software, there is no external library dependency beyond the standard OS package is required. And also if we talk about the ATK, that is a background simulation engine, and this VNL, Virtual NanoLab, that is a graphical user interface. So both calculation engine and the GUI is available for both Microsoft Windows and the Linux 64-bit operating system. And it also comes with the MPI parallelization for the faster simulation, and it comes as a floating license. Now these are the listed customers that are using this Quantum ATK. So many more universities, higher universities, central universities are using this Quantum ATK. So thank you for listening this presentation. Now I would like to demonstrate you live in this Synopsys Quantum ATK that how you can import the material, how you can do various modification, and also how you can design some of the devices structure, and then you can also apply the biasing voltage so that you can simulate their various electrical properties. So you can see this is the graphical user interface of this Quantum ATK that is called Virtual NanoLab. And here you can see this is the project section. So in the left hand side, you can see these are the various plugin toolbars. We have the project. So multiple project you can also create. If you want to create any project, you need to click on this add option. Here you need to define the directory and the project. Then you can easily create. And if you want to work on the existing project, then you can double click and then you can go to the data. So you can see this is the data filters. So these are the project that I have simulated earlier. And here we can filter out your data. Like you can see, we can filter out everything, the created structure and the simulated data. If you want to show only simulated data, you can see these are the output files. And if you want to show the bulk configuration, these are the bulk configuration. And if you want to show the device configuration, these are the device configuration. You can also create your own data filters by selecting this add option. This is the builder. That is the main part of this Quantum ATK, where we need to create our structure, and whatever the structure we will create, that will store in the stats. So this area is called stats. Here we will show the 3D view, and this is the advanced panel toolbar. So this advanced panel toolbar will help you to create your desired structure. Like you can see, we have the various builder, FM cantilever tip structure, amorphous builder, alloy builder, icosidron builder, interface builder, nanoparticle, nanowire, nodelastic band, and even we also have the bulk tool option. You can see we can repeat our cell, we can merge the cell, we can also create the super cell, lattice, and even you can see we have the device tool as well. So this is the workflow. So in the workflow, you can see we have the various calculator. We have the LCO calculator, we have the device LCO calculator, plane wave calculator, semi-empirical calculator, device semi-empirical, force field calculator, and also the ground state calculator that will combine with the many body perturbation theory. Here you can see this is the job submission settings. So this is the local machine. If you want to run the job on the remote machine, then you need to set up the remote machine first. So you can see this is the new direct remote machine, local machine, LXF, PBS, PBS Pro, ESG, and also the Solarum machine. Now this is the editor. So if you are exporting writing the script, then you can write your own script here. And if you are not aware, then you can go to the builder part. This is the V1 where you can visualize the 3D view, and this is the online database. So in the online database, you can see we have the crystallography open source database, and we also have the material project. So if you want to start from the scratch, so you need to select this builder and select this add option. So in the add option, you can see we have the new configuration. So once you select a new configuration, a default isolated hydrogen element will be added. So you can see this is the hydrogen with the fractional coordinate point 0, 0, 0. If you want to send this hydrogen with any of the element, so you can see we have the toolbar and we also have the periodic table. So this is the periodic table. Any of the element you can select as per your need, and then you can change the element. So you can see the hydrogen has been replaced by the aluminum element. Now you can see this is the from file option. So these are the supported file format that you can easily import in this Quantum ATK. Like we support the Python file, SDF file, .xyz file, CIF file, XSD postcard file, contour file. So you can easily import. And now if we talk about the database, so this is the local database where we have the molecular structure, crystal, fluorines, zeolite, monomers, and also with the ground state element. So these are the list of molecular structure. You can easily search the molecule here. Like you can see, this is the benzene molecule. And if you want to know the property of this benzene molecule, so you can see this is the chemical formula and this is the properties. Like we have the boiling point, melting point, molecular weight. This is the crystal. So we have the list of crystal material as well. We have the various lattice type like the face center, body center, rhombohedral, hexagonal. So here you can also search the material. Like you can see, this is the silicon material and this is the face center cubic structure. You can see this is the ABC value and this is the symmetry information. Here we have the element and their fractional coordinate point. We have the fluorine structure as well. So you can see these are the fluorine materials and these are the zeolite materials. And we also have the monomers for the polymer simulation. And even the importing the new monomers, that is also available. Here you can see this is the import option. So in the import option, you can see we need to define the name, their group, the type of monomers, and also we need to import the molecules. Then it will convert the molecule into a monomers. And then you can easily simulate, study for the polymer simulation. Here you can see these are the ground state element. And if you want to add any of the material in these steps, so you simply need to click on this add option. So you can see this is the silver that I have imported from the local database. And suppose the material that you want to work that is not available in the local database, then you can go with the online database. So here we have the periodic table. So in the periodic table, we need to select our element first. Like you can see, this is the hydrogen and this is the oxygen. So two element has been selected. Now you need to click on this search option. Then it will search every possible combination of hydrogen and the oxygen. Now you can see it is searching from the crystallography open source database. And similarly, you can also use the material project. You can see it has found 39 structure with the different crystal type, like the simple tetragonal, base centered, rhombohedral, hexagonal, simple cubic structure. Like you can see, this is the hydrogen peroxide. This is the lattice information and this is the symmetry information. And also this is the DY number. Now, if you want to add this structure into the builder, you need to click on this arrow and then select this builder. And you can also download this file and even you can copy this COD identifier number. So you can see this is the COD identifier number. You can go to the builder, select this add option, and you can see this is the plugin toolbars. We have the crystallography open source database for the crystal. We have the PubChem database for the molecules. So you can see it is asking to enter the COD identifier number. So we will paste the COD identifier value and then click on this download option. Then it will easily download our structure into this test, and then we can visualize the 3D view here. And suppose the material that you want to work is not available either in the local database, either in the online database, then you can create your own structure by using the plugin toolbars. So you can see this is the crystal builder that will basically help you to create any kind of crystal structure. Either you can create a triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and also the cubic structure, like the face center cubic structure and the body center cubic structure. And then you can define their ABC value, their alpha, beta, gamma value, and then you can add the element and their fractional coordinate point. And then you can see this is the preview option where we have the primitive cell and we have the conventional cell. So suppose I would like to take a face center cubic structure. So I would like to select their space group, and you can see the Brebes lattice will automatically selected, and this is our face center cubic structure. Here we can define the ABC value as per our research work. And then you can add the element by selecting this add option. So you can see these are the various fractional coordinate points. So I would like to go with the XYZ. So you can see it has selected automatically hydrogen element, and this is the structure. So if you want to change this hydrogen, you need to double click, and you can see this is the list of element. If you want to select this gold, you can see this is the gold material, and this is the conventional cell. If you want to show the primitive, you need to select this primitive and go to the preview option. So you can see this is the primitive cell. So this way we can easily create any kind of crystal by using the crystal builder. And once you're done with the crystal builder, you need to click on this build option. And here you can see we have the more plugin toolbars. We have the nanotube builder. So by using this nanotube builder, we can create a multiple nanotubes. Here you can see we have the inner tube, center tube, and outer tubes. And here you can see we have the chemical properties. So at the site we have the carbon, at the site we have the carbon. You can also change the element from the periodic table, and you can define the bond distance. If you go with the default value, you can see this is the carbon nanotube. Now you can also change the scroll vector and an M value as per your need. If you want to enable the center tube as well, you can see we have the inner tube, we have the center tube. So we have three tubes: center, inner, and outer tube. So this is the carbon nanotube. If you want to design any other nanotube, so simply you need to replace the site element. If I select this silicon element, you can see it will create a silicon carbide nanotube. And if you want to work on the MOS2 nanotube, so we need to replace both the site element. Like you can see, this is the molybdenum at the site A and sulfur at the site B. And then you can define the bond distance. For desired bond distance, you can design, and then you can go with the inner tube, center tube, and the outer tube. Now you can see this is the MOS2 nanotube. So I would like to go with the center tube, select this preview, and then click on this build option. Now you can see this nanotube is quite thin. So if you want to increase the length, you can go to the advanced panel toolbar. And in the advanced panel toolbar, we need to go to the bulk tool. In the bulk tool, you can see we have the repeat option. So we can repeat our cell in any of the direction, either direction A, direction B, and direction C. So I would like to repeat in the transport direction, that is C. So you can see 10 times in the transport direction and then apply. Now you can see the length of this nanotube has been increased 10 times in the transport direction. So this way we can easily increase the length of any structure. And now if we talk about the nano ribbon, similarly we need to define the chemical properties, their bond length, and also the passivation with the hydrogen element. Then that you can also include. And then you can go to the geometry where you can define the, either you can align with the scroll vector and an M value, either you can go with the zigzag and the armchair structure. You can see it is aligned with the scroll vector and an M value. If you want to show the zigzag, this is the zigzag structure. And if you want to show the armchair, so this is the armchair graphene nano ribbon. So I would like to align with the scroll vector, and you can also increase the length and then select this preview. So this is the graphene nano ribbon, and if you want to create a nano sheet, so you can see this is the nano sheet option. Similarly, we need to define the chemical properties, bond length, and then the scroll vector, and select this preview. So you can see this is the graphene sheet. If you want to create a silicon carbide nano sheet, so here we will select the silicon element, and here if I select the oxygen, silicon dioxide, and then you can define their bond distance, and then select this preview. Now you can see. So this way we can create any kind of nano sheet, and if you want to increase the length, you go to the advanced panel toolbar, select this repeat option. Now you can see. So this is the single layer. If you want to work on the multiple layer structure, so simply you can copy. So first you can select the element, then copy, and then you can manually paste here. And either you can go with the mirror option. Here you can see. So this way you can work on the multiple layer as well. Now if we talk about the magnetic tunnel junction, so you can see we can define the electrode element at the left side and the right side, then define the lattice constant, and then you can also enter the electrode extension layer, and then you can define the barrier materials. So in the barrier material, it will be oxide materials, and then you can define the number of layer and the separation, and then you can select this preview. Now you can see we have the iron at the left electrode, iron at the right electrode, and we have magnesium in the center region. So this is the magnesium oxide in the center. You can easily change any element from this periodic table. Suppose I would like to select the zinc at the left and right, you can see. So this is the magnetic tunnel junction. If we talk about the advanced panel toolbar, so you can see this is the FM cantilever TP structure. So for creating the FM cantilever TP structure, basically we need to drop the material, and we need to define the base size, their height and their taper height, and then we need to define the clipping method. Suppose I would like to go with the silver. You can see I have dropped the silver material in the material section, and if I go with the default value, you need to click on this build option. Then you can easily create a silver based FM cantilever TP structure. And if we talk about the amorphous structure, so for creating the amorphous structure, basically we need to define the sum formula and their density. You can see this is the SiO2 with the density 2.65. Now you can see this is the silicon oxide amorphous materials. If you want to change the material, you can change in the sum formula. You can see this is the MuS2 with the formula 100, and then you can click on this build option. So any kind of amorphous structure you can create by the amorphous builder. And if we talk about the alloy builder, so this is the Hessler alloy builder. Here you can see we have the structure type. So we have a different combination of X, Y, Z. So where X and Y are the transition element and Z is the main group element. Here you can define the lattice constant, and then you can define the formula. So this way you can easily create a Hessler alloy structure. And if we talk about the icosahedron builder, so basically we need to define the order, the bond length, and then we need to drop the materials. Here you can see from this periodic table we can select any of the element and then select this preview. So this is the gold based icosahedron structure. If I increase the order, you can see this structure will change. Now if we talk about the interface builder, so you can see this is the interface builder for the two materials. And if you want to create the interface between more than two materials, then you can go with the interfaces. So let me create the interface between two materials first. Like you can see this is the gold in the first strand, and then the silver material in the second layer. Now it is generating the interface between the gold and the silver. You can see. You can easily add the layer by selecting this add option. And you can also go to the layer settings. So in the layer setting, you can decrease or increase the layer, and these supercell settings. So this is the supercell settings. And in the supercell setting, you can see we have the graph over the number of atoms and the mean absolute strength. So at this point, you can see we have total 15 atoms. This is the area, this is the angle between the vector, and this is the rotation between the surface. If I increase the point, you can see the number of atom has been increased and also the area. If I go with this point, maximum point 154 atoms, and then you can also define the staining method. Like you can see this is the stain first surface, second surface, and both surface. Now I would like to apply. You can see this structure has been changed. So this is the interface between gold and the silver material. And here you can see we have the optimization settings. So if you want to optimize your structure before going to the builder, you need to select this toggle cube optimization, then select this preview, and then click on this create option. Then after the optimization, it will generate your structure in this test, and this is the 3D view. Now you can see this is the nanoparticle builder. So for the nanoparticle builder, basically we need to drop the material in the cell and in the core section. And then we need to define the core radius, the gap between the core and cell, and then the cell thickness. I would like to drop the material. You can see the gold in the core and the silver in the cell. Then you can define the radius, gap, and the cell thickness. And then click on this create option. Then it will easily create a nanoparticle structure. So in the core, you can see we have the gold, and this is the silver material. Now we have the nanowire builder. So for creating the nanowire structure, our structure should be the simple cubic structure, either face center cubic structure, either body center cubic structure. So I would like to take a cubic structure. Now you can see we can define the wire direction, either 100, 110, either 111. And then you can define the nanowire properties like the nanowire radius and then the surface energy. This is the nanowire in the direction of 100. If I select the 110, you can see. Now, if you want to increase the length, you can go to the repeat option. And then you can enter the value and click on this apply. Now you can see. This is the gold-based nanowire. Now, if we talk about the device simulation, suppose you can see we have created a nanotube structure. Now you can see this is the MOS2 nanotube. If you want to create a device from this bulk structure, you can go to the device builder. You can see this is the device builder, and here we need to define the electrode extension length. You can see it is automatically selected their minimum electrode length for the left and right, 5.4 angstrom. You can change the electrode extension length, and it will resolve your issue for the scattering between the electrode and the central region. Now, if you want to add the buffer region in the left and right region, you need to click on this add option. You can see. So this way we can create the buffer region as well. And if you done with this device builder, you need to click on this OK. So we have created a device, and if you want to include any kind of doping, so you can go to the doping option where you can set the N-type doping and the P-type doping. And if you want to do the elemental doping, you need to select that particular element, and from this periodic table, you can replace the element. Suppose I would like to go with the oxygen. Now you can see. So this is called elemental doping. And if I show the N-type doping and P-type doping, so for the N-type and P-type doping, we need to select the region first. Like you can see this here, I would like to select a P-type doping. Here you can see this is the doping type. We have the N-type and we have the P-type. This is the P-type. Here you can define their concentration value and then their unit. Suppose I would like to define the N-type doping in the center region. Now you can see this is the N-type. And if I select the P-type doping in the right region as well, now you can see. So this is our PNP transistor. And if you want to add the spatial region and if you want to convert this structure into a 3-pro device structure, then we have the spatial region. So here you can see we have the region type, we have the metallic, and we have the dielectric substrate region. So first, let me try the dielectric substrate region, and then we will go with the metallic gate and the source and drain. Here you can see this is the region. Now you can see we have the geometry where we have the box, sphere, and tube. So this is our MOS2 nanotube. So we need to select this tube option. Then we need to define the direction x, y, and z. Their starting point and their ending point. And then you can define their inner radius and the thickness. You can also measure the distance between the center region, and then you can easily put the point here. Here you can see we have the distance measurement. So let me measure the distance first. If I measure the distance from this point to this point, you can see this is the 66.61 angstrom. Now we will go to the spatial region, and in the z direction we will define. Now you can see. If you want to make it in centrally, then you need to define in the x and y direction as well. Suppose I would like to go with the now you can see this is in the center position. Now if you define the inner radius and their thickness, like you can see I would like to go with the 6, like you can see. Here I would like to take 1 and their inner radius as 7 angstrom. Now you can see we have created a dielectric substrate region. Similarly, you can create a metallic gate and also the drain and source. So this way we can create a 3-probe device structure, and also you can see this is the redo and undo option. Now I have already shown you the materials and the devices as well. And if we talk about the simulation procedure, so you can go with your desired materials. Suppose I would like to take this gold material for the simulation. Here you can see this is the workflow builder. So in the workflow builder, we need to set up the calculator and the analysis part. So this is the LCO calculator, and we also have the plane wave calculator. So based on your system and also the accuracy, you can select your calculator. You can see this is the LCO calculator. If you want to change any parameter in this DFT LCO calculator, you need to double click. And here you can see we have the main parameter LCO basis set. And in the main parameter, you can see we have the spin type. So if you want to include any kind of spin in your materials, like the unpolarized, polarized, non-collinear, and non-collinear with the spin orbit coupling. Here we have the exchange correlation function like the LDA, GGA, meta GGA, hybrid function, and also the custom option. We have the pseudo potential method like the non-conserving and the power potential. This is the pseudo potential like the single zeta polarized, double zeta polarized, single zeta double polarized, double zeta double polarized, and single zeta double polarized. We have the numerical accuracy where we have the occupation method. You can also define the temperature. You can also define the cutoff energy, and this is the K-point sampling method. Here you can see this is the density. If I talk about the LCO basis set, so you can see this is the predefined functional set. This is the GGA, and here you can see we have the various predefined exchange correlation function like the PB, PLYP. If I select the hybrid function, you can see HSC, B3LYP. So whatever the exchange correlation you want to select, you can select from this settings, and then you can see we have the iteration control where you can define the tolerance, maximum iteration steps, and also the damping factor. This is the Poisson solver where we have the direct conjugate gradient and non-uniform with the grid conjugate gradient to multi-grid fast Fourier transform and fast Fourier transform for the 2-dimensional. So these are the settings that a user need to define before going to the simulation. Now, if I show the analysis part, you can see these are the list of analysis properties, and we also have the optimization settings. You can see this is the optimization tree, and in the optimization, you can see you can define the fault tolerance, optimize the cell, stress, error tolerance, maximum number of iteration step, maximum step size, and this is the optimization method. Now, if you're done with the workflow, if I select some of the analysis part like the band structure, you can easily search here. Like you can see, this is the band structure. If I select the density of state, this is the density of state. If I select the projected phonon density of state something, you can see these are the phonon properties like the electron phonon coupling, phonon band structure, phonon density of state, and also the phonon transmission spectrum and projected phonon density of state. If you want to calculate the optical properties, so we have the optical spectrum. If you want to work on the Raman properties, you can see this is the Raman properties. So all the property you can simulate.
Hello,
Like
good
electrical,
evening, sir.
electronics. Yeah, good
Hello,
evening.
sir. Yes, sir. Sir, I actually am having doubt. Sir, can you show the
Yeah.
structure?
Which one? This one?
Yeah, that what to say? Tube structure na you form na dielectric and metal.
Yeah, this is the.
Yes, sir. Sir, the purple one showing na actually you increase the inner radius na, so the dielectric material should be the outer part na in that.
The dielectric region should be under the center region.
But
You
actually
can see
some
it is exceeding the electrode.
okay. Actually in some
But
research
when
paper
you
I
go to
saw
the
that.
simulation part,
Hmm.
yes.
Actually in some research paper it is outside na this purple one.
But if you go to the simulation part, you can see if I take this a device for the simulation, you can see
Yes. Okay, okay.
the spatial region extending into the electrode are ignored during the calculation.
Okay, sir. Okay, continue, sir.
Okay, sir. So this is the workflow setups. Now, once you're done with this workflow setups, you can go to the editor, and here you can define the file name and then select this OK. Now you can see this is the Python script. So in this Quantum-ATK, there is no need to write any script for any structure. Simply you can create this structure in the builder. Go to the workflow settings where you need to set up the calculator and the analysis part, and then it will easily generate your Python script. And this Python script is editable. So before the simulation, if you want to change any of the parameters and also the analysis part, then you can add that. And if you want to write your own script, then you can select this add option and you can write the script here. Now this is the Python script. If I go to the job submission settings, we need to save this Python file, select this save, and you can see this is the job submission settings where we have the local machine. For the remote machine, we need to set up the remote machine first, then it will find here. You can find here. This is the job type. You can see we have the serial. So if you run on the serial, then it will select a single core. If I select this threaded parallel, then it will run on a single processor, but you can define the number of thread. Here you can see. And in the multi-process parallel, you can define the number of processor and the number of thread as well. Either you can go with the machine settings with the automatic, or you can manually define. Like you can see 4. Here I would like to take 2 and then select the side option. This is my project, and here you can see the state is pending. So if you want to run the job, you need to select this add option. Now you can see the state has been changed and it is under running condition. Now here we will get the log file. So whatever the background simulation is ongoing, you will get the information here, and once it will be done, you will get the output file in the data section. So basically this is the procedure for simulating any kind of structure, either the material, either devices. And in the workflow setting, you can see we have the template. So if I select with the new template, new workflow, and then the template. So here you can see we have the calculator settings. So if you are not aware of any of the calculator settings, like their exchange correlation function, what should be the key point sampling, then you can go with the template. First, you can import the structure, like if I go with this graphene, and here you can see, this is the metal with the low accuracy, metal with the higher accuracy, medium accuracy, and with the higher accuracy. So based on your accuracy, you can select the calculator. You can see it will automatically select your parameter. You can see here we have the density, keep on sampling 222. If I select the higher density, you can see. And it automatically, so no need to change any parameter in the template. And in the template, you can see we also have the molecular dynamic simulation. So this is the ab initio molecular dynamic simulation, and in the quantum ADK we have the classical molecular dynamic simulation. This one. And if I go with the traditional force field simulation, suppose I would like to take this amorphous material, and in this amorphous material, so you can see we have total 1500 atoms. If I select this MOS2, we have total 300 atoms. If I select with the go with the classical force field, then within a 2 minutes it will give our output. You can see this is the classical force field, and here you can see it is showing the class. There is no parameter selected. So basically we need to select the interatomic potential. From this, either you can go with the predefined potential set, we have the bonded potential set, we have the MTP, moment tensor potential set, and we have the custom potential set. So we have the molybdenum and the sulfur in this structure. So we will go with this potential set, and here you can see there is no class. If I select the molecular dynamic simulation, you can see this is the molecular dynamic calculator that we need to add, and here you can see we can define the method. In the method, you can see we have NB velocity varlet, NBT, Langevin, NPT. Also, we have the stress strain, and then you can define the time stage and then initial velocities. You can see this is the Maxwell-Boltzmann distribution configuration velocities and zero velocities. Then we can define the temperature. So this way we can do the molecular dynamic simulation. You can also calculate the force, energy, total energy. Like you can see, this is the force. If I add the total energy, this is the total energy. If you're done with the workflow builder, you can go to the editor to generate the Python scripting, and then you can easily go to the job edge script. Then it will easily save a Python file, and then you can run the simulation. Like you can see, this is the amorphous structure. Now you can see the state is running. Now the simulation is also ongoing. Now you can see it will easily generate your output file within a 2 minutes. And if we talk about the machine learning technique, so you can see in the template, I would like to select a new workflow, and here you can see we have the moment tensor potential. Here you can see we have the crystal turning. So basically this crystal turning is the refer to the process of generating the new interatomic potential, the new material. You can see I would like to add, you can see it is added, and here you can see we have the configuration table where we have the orthorhombic, monoclinic, and also the cubic structure. You can also import your own structure by selecting this load from the file. Now you can see it is showing our structure. Now this is the Hafnia structure and this is the orthorhombic. If you want to load your own structure, you need to select this load configuration from the file. And you can see, you can create the structure in the builder, and then you will get the structure information in the right hand side. Suppose I would like to go with this nanowire, you can see. This is the nanowire. So any of the material as per your need, you can select. And then you can go with the LCO calculator. Then it will generate the force, total energy, and the stress. Then it will go to the crystal turning random displacement by the strain method. You can see. Here we can define the system size. We can define the target sample size. We can define the atomic rattling amplitude. So all these input parameter we need to define. Then it will go to the scan over nonlinear coefficient. So basically it will scan over the DFT simulation, where we can define the number of initial guesses, and also you can see this is the GPU acceleration for the faster simulation. You can also enable that. And then it will go to the moment tensor potential training, where it will generate the entire time potential in the find waste sheet. Here you can see this is the input. We will get the moment tensor potential training data. Here it will store our output. So basically this is the process for the machine learning technique. And even we also have the active learning technique that we'll find in the quantum ATK. You can see this is the active learning simulation. We also have the active learning molecular dynamics. We also have the active learning optimized geometry option. So for the active learning, we need to delete this one. We will add this active learning simulation. You can see this is showing the cross. Basically, we need to add one or two blocks like the crystal. This one we need to add. Let me check. Yeah, this one. Momentational fitting, potential fitting parameters. We will add it over the. Then we will go with the crystal turning. Now you can see. Again, it is showing the cross. So basically, we need to add the data table. You can see this is the table. We will add it over the moment tensor potential here. And here we will need to add one or two parameters. Like you can say this is the type. Here we need to define the data. It will store our data. Moment tensor. Moment tensor potential training. This one. You can see the cross has gone. So this way we can also do the active learning simulation. And even the polymer simulation, you can see we have the polymer builder. You can see this is the polymer builder, where we need to select the polymer type like the homopolymer, copolymers, and also we need to define the force field calculation, and then it will easily generate a polymer structure. Like you can see this is the polymer sequence, where you need to define the number of monomer per chain, number of the chain, and this is the homopolymers. You can see we will select from the database. Now you can see this is the database of the monomers. You can select any of the monomers. You can define the tactic ratio, and here if you want to define more than one monomers, then you can go to the random option. And you can see this is the polymer environment, where we need to define the polymer density. If you want to add any of the like a host configuration, like some of the bulk configuration, like the nanoparticle something, then you can add that here. And if you want to add the molecule, you can also add from the add molecule from the file option. And here you can see this is the pre-equilibration, where you can define the temperature and the molecular dynamic steps for force kept simulation. And then you can define the force field. You can see we have the drying OPLS minimum universal, and then you can define the electrostatic accuracy. then it will easily, you can see the cross will go on after defining the monomers. So this way we can also create the monomer structure. You can see. And even we have the magnetoresistance, RAM, IK metal gates that we will get in the data. You can see. This is the high K metal gate stack builder, MRAM builder, nanowire builder as well. If I show some of the data, you can see. First I will show you the, yes, you can see. This is our amorphous structure by using the classical force field. You can see within a 2 minutes, it is simulated our data. Now this is our project file name, amorphous prebuilder output 10. We will go to the data, and here we will, yes, this one. You can see we have performed the molecular dynamic stress, and we have simulated their force and the total energy. First, let me show the molecular dynamic output file. Then we will find the graph over the temperature, volume, density, and also with respect to time. You can see. This is the molecular dynamic simulation. So here you can see this is the temperature, and we have the potential energy. If you want to show the changes during the simulation, you can see. You can see some of the changes are ongoing. So this is the visualization in the movie form. This is the overlay. And also you can simulate the total energy, pressure, density, and the volume. And then you can find the graph. If I show the other simulation as well, like you can see we have a device simulated data. This is my device configuration where I have the silicon PN devices. And I have simulated their projected density of state and also the Hardy potential. And also I have simulated their transmission spectrum. So this is my structure. We have the left electrode, right electrode, and this is our center region. Now, if I show the data, this is the Hardy difference potential. This is the projected density of state. If I show the graph, you can see. This is the projected density of state. Here you can see this is the spin type where we have selected total spin. This is the energy spectrum. Now, if I show the transmission spectrum, so let me cancel this and then open this transmission spectrum. So I have shown you the maximum properties of this Synopsys quantum ATK software. So if anyone has any query, then you can unmute the mic and ask me the query. So I will try to.
Hello.
Yes, sir.
Yes, sir. Is the session complete, or will you tell something regarding more?
Yeah. I'm going to conclude this session.
Okay,
So
sir.
if before this, if anyone has any query, they can ask.
Yes, sir. I am just asking regarding that. Just wait for
Yeah,
1 minute.
tell me, sir. So this is the transmission spectrum graph. So this is the spectrum with respect to energy, and this is the coefficient with respect to K. And this is the K point sampling. We have the fractional Cartesian, and here you can see this is the transmission at 0. If I show the spectral current, this is the spectral current where we have the total spin, and this is the current value. Here you can also change the electrochemical potential, and also the right chemical potential, and also the temperature. Yes, sir. Tell me, sir. And if you want to know more about this quantum etiquette, their manual and their tutorial, you can visit this Synopsys quantum etiquette documentation. Here you can see we have the tutorials, we have the manuals, and we also have the publication papers. This is the tutorial. You can see semiconductors, battery and energy storage, complex interface, 1D nanostructure, 2D material, and we also have the manuals. So if you want to know more about the background theory, like this is the DFT, you can see all the theory and their equations are mentioned. So whenever get the time you can visit, then I hope you will be more familiar about the procedure and also about the
Yeah, hello, good evening, sir.
Yes, sir. Good evening.
Sir, can you tell something? Can we design memristor from this? Quantum etiquette
Yes,
means
you can.
memristor
Yes, you
design,
can
sir.
also design the. Yes, yes.
Okay. Can you refer some ideas, sir, how we can go for that?
Yeah, you
Means,
can see this is the emblem builder. We also have the tutorial part where you can get the step-by-step procedure.
okay, sir. If you have something, kindly show it.
Yes, yes, I am going to show. You can see. Yeah, all the process are mentioned. Now you can see. Actually, it is running one of the program in the job setting.
Yeah, no issue.
Even you can design from this data section. You can also go with this workflow settings. Yeah, you can see. This is the magnetoresistance RAM builder, where we need to select this add option to add the layer. So more than one layer we need to require. We require.
If you want to ask
You can see this is a crystal. We have the magnesium oxide, tungsten,
it's
also iron, cobalt, and iron. If I select one more layer as well, you can see. If I change this with the iron cobalt, now I would like to add more layers. And here I would like to take iron. You can see this is the alloy and we have the crystal. Now if I show the structure, you need to click on this update. Then it will show a graph for number of atoms and the mean absolute strength. You can see this is our first layer where we have the magnesium oxide with the 100 surface. So at this point you can see we have total 34 atoms and this is the total layer. If I select this point, you can see. So this way you can create a structure and then you can select this arrow, go to the builder. Now you can see this is our design structure.
And
And
sir,
then
where
we will go to the workflow.
yeah,
Yes,
sir, where you got the AMRAM builder?
you can even get the data section.
Okay.
Let me show. This is the MRAM builder. And even you can also find it in the workflow setting. Here you can see. This is the magnetoresistance RAM builder.
Okay.
You can create a new workflow by selecting the side option. Select this magnetoresistance RAM. You can see it is showing the cross because we have not selected any of the block. So we need to double click and then we need to add the layer of the material.
So one more doubt, whether we can
Yes,
observe
yes,
the
yes.
electrical properties of the system?
Yes,
Means
yes. So for
voltage
the
and
electrical
current.
properties, yeah. So for the electrical property, first you need to convert this structure into a device. Like you can see, we will create a device.
device.
Sorry, I think some of the preview. Let me. Cancel. Yeah. This is the device from the bulk.
Hmm.
So once you create a device, then you can study their electrical properties. You can see we have the electrode, left electrode, right electrode. This is our left electrode, right electrode. This is the center region. Yes, this one. And then you can select this, okay? You can go to the workflow builder. You need to select the calculator, device calculator. And then you can go with the optical properties. Like if you want to simulate the IV characteristics, here we have.
Okay.
Yeah, you can define the gate to source voltage, drain to source voltage, their minimum point, maximum point, and also the point. In the meantime, you can also add the transmission spectrum. And if you want to know or add more analysis part, you can see. So these are the list of analysis properties.
Okay. Okay.
So
Thank
may I
you.
know any more query?
Yes, sir. Thank you so much for your guidance. Sir, we may now conclude the session.
Yeah.
Thank you so much. Thank you, sir, Deepak sir, for your guidance and support. We will continue with Deepak sir in the next. Sir, tomorrow you will be taking the session also. Right?
Tomorrow,
So
yes.
tomorrow we will have hands on this tool. So we'll meet again at 9:30 morning. Okay. Thank you,
No, ma'am, we have
participants.
the session at 4:30 p.m.
Yes, sir. Actually, other participants need to come at 9:30.
Yeah.
Your
Okay,
session
okay,
is
ma'am.
on 4:30. Thank you. Thank you so much,
Yeah.
sir.
Okay, sir. Okay, ma'am. Okay. Thank you so much. Thank you.
Thank you, sir.
Yeah, thank you all for joining this presentation and demonstration. So you can let me know whenever required any support. This is my contact details.
If you need any.
Yes, sir. Just wait 1 minute.
Yeah, you can take this snapshot. Yeah, from my side, thank you so much to all of you for joining this presentation and demonstration on this Synopsys quantum ATK.
Thank you, sir.